Well, happy 2021, everybody. Welcome back to second semester. And boy, we are going to blitz through these chapters. We only have 3 chapters to do. 2 of them are pretty short. I'm doing them a little out of order from how the book has it, but that's fine. We're going to do chapter 10. It'll be a short one, just a 2-weeker. And then we'll do another short one. And then we'll do our biggest final chapter. And then that's it. So 3 chapters and we're done. So we should be finished with this right about first week of March, second week of March, and then we've got the rest of the time to get ourselves ready for the AP exams. So so proud of you and everything you guys did first semester, and really looking forward to the second semester with you. All right, we're going to focus on different 3 different kinds of functions and their derivatives. So parametric functions, functions expressed as vectors, and polar functions. So we'll kind of take those chunk by chunk. We'll learn how to do the derivatives of each of those, how to do integrals with those, and then how those apply to other real life applications. So let's start with parametric. We're going to review the difference between a parametric and a Cartesian form of an equation, and then we'll learn how to do the first and second derivatives of parametric functions, and then, apply those to tangent lines and concavity and stuff like that. So just to review, a Cartesian curve. A Cartesian curve is a direct relationship between x and y. And so most often, those are expressed as y equals and then some sort of function of x. Now, it doesn't have to be that way. That's just the most common, especially when you're using your calculator. It'll be in a y equals format. But, we could see x minus 2 squared plus 2y squared equals 5. That's also not it's not a y equals format, but it's a relationship between y and x. So the difference is that a parametric curve is an indirect relation. Whoops. Indirect. So y and x aren't related to each other directly. They are each related independently to a parameter of t, t standing for time. So x is expressed separately as a function of time, and y is expressed separately as a function of time. And what this allows you to do is to investigate the behavior of x independently from the behavior of y. How if I just change the x part of this, or I just change the y, it won't have an impact on the other variable. So it is advantageous for when you want to isolate the behavior of different variables rather than having them affect each other. So we can go back and forth. We can go from Cartesian to parametric and the other way. So, for example, if we're given this parametric equation where x is related by the square root of t and y is t minus 2, how could we put that into Cartesian form, and then what would the graph of that look like? So the way you want to do that is you want to isolate t in this x equation. And so rather than x equals the square root of t, we would say x squared equals t. And then we would replace that. And so y is going to equal x squared minus 2. So this is going to create for us a parabola. So in Cartesian form, we're very familiar with this as a parabola, where the parabola is in Cartesian form, moved down 2 on the x-axis and opening upward. Okay, so that's the Cartesian expression. However, we are limited by a time interval here, and time is going 0 to 4. Now, that's not the same as x going from 0 to 4. That is time going from 0 to 4. X is part of the interval going from 0 to 2. All right, because if time is 0, x is also 0. But if time is 4, according to the Cartesian definition for x is 2 then. So we are only going from 0 to 2. So the way we draw this graph now is not the entire Cartesian expression. Okay, not the domain is no longer all real numbers. So let's see here. Whoops. Fill this back in. We're going to start at -2. Do it in a different color. And then we're going to end when x is 2, which puts us up here. And so that's as much of the parametric graph that we're going to do. So the initial point is 0, -2. The terminal point, terminal meaning the ending, is 2, 4. And then the direction, we show that we are moving in an upward, following that positive curve of the slope. Okay, so you're only drawing a portion of the Cartesian graph, the parametric graph. Here's another really common parametric curve that you will probably recognize more in its Cartesian equation. So we're dealing with trig here. X is defined as the cosine variable and y is defined as the sine of t. We know that the relationship between sine and cosine is the following identity. Sine squared of t plus the cosine squared of t is 1. Well, if sine squared of t, we could replace that with y squared, and cosine squared of t, x squared. And so then we get the Cartesian equation, which is more commonly recognized as x squared plus y squared is 1, which is a circle. And this circle has radius 1. And we're looking for time to be on the interval of 0 to 2 pi, which is a full rotation of this circle. And so when we want to sketch this, we're just going to sketch a circle of radius 1. Ooh, a little too far. Starting at 0, going around to 2 pi. Okay, the direction going counterclockwise. And the initial and terminal points are both 1, 0, being the same because it is a full circle. Now, if we throw a coefficient in front, so now x is 3 cos t, now we're looking at things a little bit differently because cos t by itself is x over 3. And so if we put this into the Pythagorean identity, we're going to have y squared plus x over 3 quantity squared equals 1. Now that's no longer a circle. Or x squared over 9 plus y squared equals 1. So this is now an ellipse. It's not a circle of radius 1. It is an ellipse with a major axis of radius 3. 1, 2, 3 on the x-axis here. And also, so that is called the major axis. The minor axis of y on y is still 1. And so this is now an ellipse coming through here. Direction still is counterclockwise, and we're doing a full 0 to 2 pi interval. So the initial and the terminal is the same, and it's the 0.30. Here's some better drawings than what I did of the Cartesian equations you just saw. All right, so now let's talk about the calculus of it. How to find the derivatives. The first derivative is pretty easy. Since x is described as a function of t, then x prime is dx dt. And since y is described also as a function of t, then y prime is dy dt. So to find dy dx, you take dy dt and you divide it by dx dt. Remember that the math on that is dy dt, divided by dx dt. Remember, when you divide, you multiply by the reciprocal. And so if we flip this and we multiply by the reciprocal instead, so multiply by dt over dx, of course you can see the parameter eliminates, and that's where we get dy dx from. So taking the derivative of a parametric is simply dividing the y derivative with respect to t divided by the x derivative with respect to t. Now, taking the second derivative is a little trickier. Okay, taking the second derivative, you need to find the derivative of what you just found. And the only way to, now that you've eliminated, okay, so you need to find that with the quotient rule. So you're going to find the quotient rule if needed, if you end up with something other than 1 in the denominator. But you have to divide that by the original x prime. Okay, notice that it is not a prime or anything. You have to do the quotient rule to the first derivative, but still divide it by the second derivative as well. So that's a little bit trickier. That's more people make more of their common mistakes there, so we'll practice that. First derivative is usually not a problem. It's the second derivative people get a little bit confused. They usually forget to divide by the dx dt. All right, so let's practice that. So now we're going to use our derivatives, our parametric derivatives, to do the same kind of things that we have done previously. So we're going to be finding tangent lines, horizontal slopes, vertical slopes, concavity. Okay, one comment here, there is a typo in the notes, so just cross out the 2. We don't want that. I just didn't reprint the whole notes just for that. Okay, so we're going to find the tangent line to that parametric curve, which means we need a point and a slope. So we'll start with our point. Our point will be the secant of t and the tangent of t. All right, secant t, tangent of t at pi fourths. So the secant of pi fourths is the reciprocal of cosine, so 2 over rad 2. And the tangent of pi fourths is 1. To find the slope, we will need the first derivative, so we'll need dy dt divided by dx dt. So dy dt is the derivative of tangent, so secant squared. Dx dt is the derivative of secant, which is secant tan. So reducing, we get secant over tangent. And simplifying, we'll have 1 over the cosine of t divided by sine over the cosine of t. All right, so we'll multiply by the reciprocal. 1 over cosine of t times the cosine of t over the sine of t, so 1 over the sine of t. So the reciprocal of the sine of t, which is the cosecant of t. All right, and we want to find this at pi fourths, and so 2 over the square root of 2. All right, so my tangent line, now just using the point and the slope that I found, y minus 1, 2 over the square root of 2 for my slope, and x minus 2 over rad 2. Okay, so pretty standard, straightforward. We just are, knowing how to do the rules for the derivative of parametrics. Good way to start the new year. All right, find the points where the tangent line to the parametric curve might be horizontal or it might be vertical. So first we want to find our slope. So our slope, dy over dt over dx over dt. So the derivative of y with respect to t would be 3 cos t. And the derivative of x with respect to t would be negative 3 sine t. So we're looking at negative cosine of t over the sine of t. I could simplify that to cotangent, but you'll see in a minute why I'm not going to. I'm going to leave that with a distinct numerator and denominator. So if I want to find a horizontal slope, I'm going to take that derivative and set it equal to 0. If I want a vertical slope, I will take that derivative and set it equal to 1 over 0. So the negative cosine of t over the sine of t set equal to 0 over 1, which implies that x would be equal to, okay, every time now that the cosine of t would be 0. So pi halves, 3 pi halves, 5 pi halves, etc. Okay, all of those values, not x, t. So every time time is one of those parameters, we will have a horizontal slope. Vertical slope will be similar. Except we'll set it equal to 1 over 0, which implies when the sine is equal to 0. So that will happen at the parameter values of 0, pi, 2 pi, etc. So now if we need to find an actual point, okay, points where this is happening, we need to find the x and the y. We don't just want to find the parameter, the time at which it's happening. We want to find the point values, which means we need to plug our time parameter back into both the x and the y value. So let's find a point for horizontal slope. If I plug pi halves into the x value, so the time at pi halves, I'll get negative 2 every single time. And if I plug pi halves into the, or 3 pi halves or 5 pi halves, okay, we're going to have some different values here. If I plug pi halves in, then I will get 1 plus 3. If I plug in 3 pi halves, I'll get 1 minus 3. And so I'm going to have two different values here. So I will have either 4, but I'll also have negative 2. So those are the points at which this equation would have a horizontal slope. For a vertical slope, we'll plug in the parameter of 0. If I plug in 0 or 2 pi or 4 pi, then the cosine will always be 1. But if I plug in an odd value of pi, so pi, 3 pi, 5 pi, etc., then my cosine value would be negative 1. So I'm either going to have x values of 1, or I will have x values if I have a negative 5. Now the y values are going to stay consistent. If I plug 0 or 2 pi or whatever, I'm always going to have 1 as my y value. So those are the 4 points. These are around the edges of an ellipse, because if you look back at this, this is going to form an ellipse. So these are the north, south, east, and west poles of the ellipse, and this is where we'll have horizontal or vertical little tangent lines to this parametric curve. All right, last one. How about inflection points for the same parametric curve? All right, so we need to find the second derivative. So the second derivative is the dy dx we just found, the prime of that, divided by the original dx dt. And so we look back at what our, we have negative cosine t over sine t. Now at this point I will say, all right, that's equal to negative cotangent t. All right, so I want the derivative of negative cotangent t, which is negative cosecant squared of t, divided by the original dx dt, let's look back at what that was, is negative 3 sine t. So if we simplify this, we are going to have 1/3, so positive cosecant cubed of t. And we want to find the inflection points for that. So we're going to set this equal to 0. And also equal to undefined. So 1/3 sine cubed of t being equal to 0 over 1, or 1/3 sine cubed of t being equal to 1/0. And there are no solutions here, but when I set it equal to undefined, we get the parameters of 0, pi, 2 pi, etc. So that will be the place where the concavity is going to change. And hopefully you can picture that. That would be on the east and west poles, if you want to call it that, along the major axis, the horizontal axis of this ellipse. And that's where the concavity changes from concave up to concave down. So if we want to actually know the point, we'll plug the parameter of time back in. So if I plug 0 or 2 pi, or, okay, again, this is going to give me those east and west poles. So I either have 1 or I have -5, and then the y value is 1. All right, so I hope that is enough to get you started on parametric differentiation, and we'll be together, some of you, in person on Tuesday at 11. So I'll look forward to Zooming with some of you, but seeing some of you in person, and wishing you a Happy New Year then. All right, hope you have a good start to your week. Thanks. Bye.